Come on, guys, spin harder. It burns!
Hey, have you guys heard of Spintronics?
Spintronics? Isn't that what we're doing right now?
No, man, it's way less painful. Let me tell you all about it.
Spintronics, or spin electronics, is an exciting new technology that utilizes the spin of an electron to manipulate data. In this case, spin does not strictly refer to physical rotation around an axis, but rather a quantum mechanical phenomenon referring to the particle's intrinsic angular momentum. The alignment of electron spins in a material gives rise to magnetism. Thus, the ability to control and manipulate these spins opens up a world of amazing possibilities. Discoveries in the world of spintronics have included giant magnetoresistance, spin FETs, spin LEDs, spin tunneling diodes, and spin laser diodes. Work with giant magnetoresistance earned Albert Fehr and Peter Grunberg the Nobel Prize in 2007, and the results can be found in your hard disk drive. Through GMR, smaller magnetic fields can be detected, leading to a 1,000-time increase in storage capabilities. GMR material is made of alternating layers of ferromagnetic semiconductors and non-magnetic tunneling barriers. When the electron spins are not aligned, resistance is large and the electron cannot enter the next layer. When an external magnetic field aligns electron spins, this reduces the resistance of a material and allows electrons to pass through. Remember those FETs and diodes from your physical electronics class? There are Spintronics versions of those too. Instead of manipulating electric charge, these devices operate using spin-polarized current. The ability to control individual electron spins to carry information leads us to the world of quantum computing. While presence and absence of charge provides a means of storing information in binary form, electron spin is a quantum variable that can take on a value of upspin, downspin, or a superposition of the two, thus an infinite number of possibilities. This variable is called a quantum bit, or qubit. The qubit can be visualized as vectors that form the Bloch sphere. Every point on the sphere is a possible state that the qubit can assume. When we measure the state of a qubit, it collapses into either an up state or down state with probabilities given by alpha squared and beta squared. When measured, a qubit holds the same amount of information as a classical bit. The power of a qubit comes from the infinite number of states it can exist in. This information is hidden, but can be manipulated through quantum algorithms. An example of the power of quantum computing is Shor's algorithm, which could break the RSA encryption that protects our internet identity in a matter of minutes. Scientists have also done research using electron spin to carry information through diamond wires. Since a diamond lattice does not contain any unpaired electrons, it needs to be doped with some impurity, typically nitrogen, to introduce unpaired electrons that can carry spin. Even though the electrons don't move down the wire, after all, diamond is an insulator, the spin of one electron can be passed down the diamond wire from electron to electron. This results in a flow of information, which can be read by observing the movement of a small magnet at the end of the wire. All this without any heat loss. If you didn't understand any of this, that's okay. As Richard Feynman says, I think I can safely say that no one understands quantum mechanics.